This is section 5.3, trigonometric functions of any angle. So if you'll just take a few minutes to read some of these definitions in the paragraph below, and you might want to pause the video to do that, and then we can move on to some examples. I will go through a few things. We have already addressed the definitions of the secant and the cotangent and the tan. And we already understand that we used so, ka, toa. So for example, let's just look at the tangent is equal to the opposite over the adjacent side. Now we're simply putting y and x on the graph so we can work with any angle. Okay, so you can see here where we have x and y, and then this radius is always positive. So I want to make sure x and y could possibly be negative in some of our examples, but the radius is always positive. So the definitions that we've been using for acute angles can now be extended to angles that are not acute. We've also gone through that the hypotenuse, we had x squared plus y squared equals r squared. So when we take the square root of both sides, we have r is x squared plus y squared. Since r is positive, we don't have plus or minus, since r always has to be positive when we take the square root of both sides, like we do in algebra. So we discussed what the horizontal leg is here, and the vertical leg is y. We've been doing that all along. And now, relative to angle theta, this is what we talked about in the previous video. These angles named as opposite and adjacent have to do with being referred to theta. So it's opposite of theta. Okay, let's take a look at this little chart here. That might be a little bit overwhelming, and I have kind of a neat way to remember this. So let's see if I can copy that, and then I don't have to redo that. Put that right here. Okay, so if you could just remember this, starting in quadrant 1, of course, remember this is quadrant 1, quadrant 2, and we always use Roman numerals for quadrant. You don't want to say quadrant 2, okay? So, and then quadrant 4. So we will, that did not look good. So we'll always start here and then go around to count our quadrants, okay? So why did I show you all of this? Because here's a great way to remember the signs of our trig functions in every quadrant. All students take calculus. It's kind of fun, but what does that mean? That means that in quadrant 1, all trig functions, whoops, I want to use a different color. All trig functions are positive. Now, when you go to quadrant 2, look at the S, only the sine is positive. What do you look here? The take stands for the T, only the tangent is positive. And then going to quadrant 4, the C for calculus, you guessed it, cosine is positive. And that's the only trig functions that are positive. in these quadrants. Now we have to be careful because I said all of these trig functions, but remember there's some associated trig functions as well. Keep in mind that if the cosine is positive, 1 divided by the cosine is positive, so the secant would also be positive. So make sure you go through all of that, and you can actually see that over here, that only all functions are positive, only the sine, only the tangent, and only the cosine. So it makes it really nice. We'll be using that a lot. Let's start with our very first example in this section. And they asked us to let a point P at 20, negative 21 be on the terminal side of angle theta drawn in standard position. And they want us to find the sine and the cotan of theta. Okay, so let's just go ahead and get our sketch drawn. Let's see if I can do a little bit better job with that. Not doing a very good job here. Okay, and then what do we have? We have to plot this point, which is at 20 and negative 21. So we'll be here, negative 21, 20, and there is our angle that is generated is here. So we will have this angle be our theta, okay? Keep in mind that this is also R. This side is R, okay? So what do we know for sure? We want to use the Pythagorean theorem first, and that will really help us with this. So if we use this Pythagorean theorem first, we can write that since x is 20 and y is negative 21, we know that r squared is 20 squared plus negative 21 squared. And actually, why don't we just go ahead and write that r is the square root of those. And then you can put that in your calculator and see that r is 29. So that makes it really nice now for us because we can, see if I can make this just a little bit smaller. Now we can go ahead and use our properties. So we'll work on the sine of theta first. The sine of theta, remember, that's the opposite over the hypotenuse, so that's y divided by r, and that's equal to negative 21 divided by 29, and we have negative 21/29. Now, what did you notice? Did you expect the sign to be negative in quadrant 4? Yes, the sign is negative because the only trig function that is positive in quadrant 4 is the cosine. Okay, so we expected that to be negative. Okay, let's go ahead with the cotangent. Remember, the tangent is y over x, so the cotangent is x divided by y, and we have 20 divided by negative 21. We get a negative 20/21. Angles with terminal sides on the coordinate axes are termed quadrantal angles, and in the case of these angles, ratios with x equal to 0 or y equal to 0 in the denominator are undefined. So you do want to make sure you keep that in mind. So let's take a look at this example. And find the sine, cosine, and tangent for the angle theta equals 90 degrees. So I'm going to go ahead and just use our little 90-degree angle. And of course, we can write that. And so for a 90-degree angle, what do you notice? you notice that, we're right here. And what do you notice? That x is equal to 0 and y is equal to 1. Put this right here. And so what do we have? We have that r is the square root of 0 squared plus 1 squared. So r is equal to 1. So now we can go ahead and find the sine, the cosine, and the tangent of 90 degrees. So we'll start with the sine of 90 degrees. And remember, the sine is y over r. And that's going to be equal to 1 over 1. And that's equal to 1. The cosine of 90 degrees is x over r. And that's equal to 0 over 1. And of course, that's equal to 0. And we have the tangent of 90 degrees. And the tangent is y over x. And what do you notice? That would be 1 over 0. And we cannot have 0 in the denominator, so the tangent of 90 degrees is undefined. So now we will determine reference angles. And reference angles, they can be quite simple, but you have to practice this. And once this is practiced a few times, you'll be able to work any of these problems. Some of these diagrams below are not written properly. The printing didn't come out, so I'll make sure to correct these when we get there. Okay, so let theta be an angle in standard position. Now we're going to define the reference angle, and the reference angle is going to look like that. The reference angle for theta, though, is the acute angle. So our reference angles are always acute, and it's formed by the terminal side of theta and the horizontal axis. Most important thing, we will always bring that angle up towards the horizontal axis. What if you start off with an acute angle? As you can see, theta is acute here. So what happens? Theta, the reference angle, is just equal to theta. Okay? What do you notice here? Theta is not acute. It is greater than 90 degrees. So what are we going to do? Because this is our reference angle. So what are we going to have here? I'll write it above. We are going to, in order to find our reference angle, we're going to have to take 180 degrees and subtract theta. Or if you are in radians, you will take pi and subtract theta. So I'm just going to go ahead and cross that off. Okay, and I'll cross this one off too. I'm sorry that that didn't print nicely. So now let's take a look at this next example. Look at theta, definitely not acute. So how would we get this reference angle, theta here, prime? How would we find theta prime? Well, we could take theta, which is all of theta. We could take all of theta and we could subtract 180 degrees in order to find theta prime. Yes. So then what would we have? We would also have theta minus pi. So we could go ahead and have either one of those. So what do? We just cut this part off and we're left with our reference angle. Okay, now let's take a look at our reference angle here. As you can see, here is theta prime right here. And so how are we going to do that? Well, we could take all of 360 degrees and then subtract theta. And then that would give us our reference angle. Or if we are in radians, we could take 2 pi and subtract theta. So those are your definitions of your reference angles. I would take them one at a time by drawing a sketch. Let's give some of these a try. So instead of memorizing, just try to understand from your sketch. So I'm going to go ahead and make a sketch here. And I think I'll go ahead and copy that. Here a few times. And then we'll be ready to go. Okay, so in this first example, 3A, we're looking for the reference angle. So we want to find the reference angle given theta. So here, 225 is what theta is, okay? So let's go ahead and find 225. Yes, we're beyond 180, and we keep going, and we'll hit, about right here, okay? So now we'll go ahead and draw that, and this is actually theta. But what do you notice? This is theta prime. So this is the angle that we are looking for right there. So what do you notice? You notice that theta prime is going to be equal to the theta that they gave us minus 180 degrees. And they gave us theta as 225. And 225 minus 180 is 45 degrees. So if they give us theta in degrees, we will answer in degrees, okay? Let's give this next one a try. 11 pi over 6. It is actually just less than 12 pi over 6, which is 2 pi. So we are almost all the way around. We're about right here. And this is what we're looking for right here, this angle here, which is theta prime. And of course, this green is theta. So what would we do? Theta prime this time is going to be all of 2 pi minus theta that they gave us. So 2 pi minus 11 pi over 6, and that is pi over 6. Okay, let's look at example C. Negative 2 pi over 3 is theta. So remember, we're going to go clockwise now. And if we're going to go 2 pi over 3, we'll go all the way about right here. And of course, this is theta. And our reference angle this time, remember, we need to go to the x-axis. That is going to be theta prime. So how are we going to find theta prime? Our reference angle, just looking at that, what do you think we'll do? We will take how many pi over 3's, or we can go ahead and take 4 pi over 3 if we'd like. I think the easiest way would be go ahead and use a different angle here. So as you can see, what do you notice? Negative 2 pi over 3 is the same as 4 pi over 3. So now we can say that theta prime is equal to, whoops, is equal to 4 pi over 3 minus pi. And that would be equal to pi over 3. So some of these can be tricky if you can take your negative angles and go ahead and make them into something positive after your sketch. That might help you. Now, what do you notice about D? That is greater than 360 degrees. So we have made more than one rotation. Since it's positive, we're going to go ahead and go 360, and then you guessed it, 30 more degrees. And now we will, whoops, so we will go around once and come back 30 degrees, and our reference angle will be this angle right here, and that's theta prime. Okay, so what will we do there? Yes, you guessed it. We will have our reference angle equal that 390 degrees minus 360. So the reference angle will be 30 degrees. Now let's evaluate trig functions using these reference angles that we just worked with. So what are we going to do? We're going to first find the reference angle, okay? So we're going to first find theta prime. And after that, we are going to check the sign. Is it positive or negative where theta lies, okay? So let's start with number 4. Use reference angles to find the exact value, okay? So let's go ahead and begin with our sketch. And I'm just going to go ahead and make a few of these. And you can maybe be doing the same. Okay. Let's go back to number 4, cosine of 135 degrees. So let's get that first on our graph. And what do you notice? If we're at 135 degrees, we're not quite to 180. Again, this doesn't have to be perfect. And this is going to be 135 degrees. So what do you notice? If we are in quadrant 2, the cosine is going to be negative, okay? So we do need to make sure we're aware of that. In fact, I will just move this down a little bit, and I will put equals, and we already know we're going to be negative, okay? So now what are we working with? We want to find that reference angle, which is right here. And in order to find that reference angle, we will take 180 degrees minus 135 degrees, and you can see that theta prime is 45 degrees. So now we will find the cosine of 45, and actually we can put that right up here. This is the opposite of the cosine of 45 degrees, and that's the opposite of root 2 over 2. Okay, let's take a look at number 5, the sine of 240 degrees, and 240 degrees is past 180, about right here, and this is 240 degrees. This is our reference angle right here, theta prime. And in order to find theta prime, we will have all of 240 degrees minus 180. And we will have 60 degrees. Now, the sign in quadrant 3 is negative, okay? So in quadrant 3, the sign is negative. So I'm going to go ahead and put that negative there. And now what can we do? This is the opposite of the sine of 60 degrees. And that would be the opposite of root 3 over 2. Okay? Keep in mind that we have already made a table of these values. From the previous section, 5.2. So you could make that table. Okay, moving on to number 6, the tangent of 5 pi over 6. And if we have 5 pi over 6, we are not quite to 6 pi over 6. We're about right there. And we notice that in quadrant 2, the tangent is negative. So we already know we are going to have a negative there. How do we find theta prime? We will have all of pi minus 5 pi over 6, and that's pi over 6. So we have the tangent of pi over 6 with the negative in front of that, and that's the opposite of root 3 over 3. Okay, the cosecant of negative 11 pi over 6. So if you take a look at negative pi over 6, negative 11 pi over 6, you go almost to 12 pi over 6. Okay, so this is negative 11 pi over 6. So that reference angle right here is going to be equal to all of 2 pi minus 11 pi over 6. And yes, that's pi over 6. So we also notice that in quadrant 1, the cosecant is positive. And why is that? All values, right? All students take calculus. So in quadrant 1, all of our trig functions are positive. So now this is just equal to the cosecant of pi over 6, and that is equal to 2. Okay, moving on to number 8, we have the cotangent of 540 degrees. And yes, 540 degrees is starting here, starting here and going around, and going all the way to this x-axis here. How do I know that? Well, this is 540 degrees, and our, theta prime is going to be 540 degrees minus 360. and we get 180 degrees. So this here is theta prime. So what do we notice about the cotangent? The cotangent of 180 degrees. Remember, we're on the axis, and the cotangent of theta is equal to 1 divided by the tangent of theta, and that tangent of theta is equal to 0 because, so that'd be the cosine over the sine, and we know that the sine is 0 there at 180 degrees. So this is undefined. Looking at number 9, the secant of 5 pi over 3. So we have 5 pi over 3 almost to 6 pi over 3. And this is 5 pi over 3. And then we have our reference angle, which is theta prime. And theta prime is going to be equal to 2 pi minus 5 pi over 3. And we have pi over 3. Now, in quadrant 4, if we have the secant, in quadrant 4, all students take calculus. So in quadrant 4, the cosine is positive. Therefore, the secant will also be positive since the secant is 1 divided by the cosine. So we will just have the secant of 5 pi over 3 is equal to the secant of pi over 3, which is just equal to 2. Okay, find two angles between 0 and 360 degrees where the cosine of theta is equal to the opposite of the square root of 3 over 2. So keep in mind that we have, let's go ahead and just sketch this on there. We have 1 here and 1 angle here. Whoops. Okay, why is that? Because that's the opposite of the square root of 3 over 2, and we recognize those angles that are negative. The cosine is negative. In quadrants 2 and 4. Okay, so in quadrants 2 and 4, we have those angles there that we need. So we will go ahead and have 180 degrees minus 30 degrees, and that's equal to 150 degrees. And remember, this square root of 3 over 2 corresponds to the cosine of 30 degrees is root 3 over 2. So that's how we know that these angles are both 30 degrees. And here we have 180 degrees plus 30 degrees, and we have 210 degrees. Okay, so now we can say that theta is equal to 150 degrees and 210 degrees. Okay, looking at number 11, the sine of theta equals the opposite of the square root of 55 over 8. Now that's not something that we recognize, so we will have to do a little work, but that's okay. So we'll go ahead and have our sketch here, and we will have the y coordinate as the opposite of 55, and then we will have 8. Whoops. 8 here. Now, why did I choose that? Because what do you notice? We're looking for where the cosine is negative. And the cosine is negative in quadrants 2 and 3. But because we have the opposite, a negative root 55, we know we're going to be in quadrant 3. So actually, we could write both of these things out. Let me do that. The sine is negative, and so that was that negative right here. And the cosine is negative in quadrant 3. So that's why we know we are in quadrant 3. Okay, so now we can put our x value here, and we can use our Pythagorean identity. We have x squared plus the opposite of root 55 squared is equal to 8 squared. So x squared plus 55 is 64. We get x squared is 9, and of course x is equal to 3. So this x is going to be negative, okay? So keep in mind, we have x is negative 3, as you can see, negative 3. X is negative, and the y is negative. Y is the opposite of the root 55, and of course our radius is always positive. So now if we want to go ahead and find the cotangent of theta, we will have, let's go ahead and find the other one first. We'll have the cosine of theta. Remember, that's the adjacent over hypotenuse. And so that will be negative 3 over 8. Now we can find the cotangent of theta, and we have the tangent of theta is opposite over adjacent. So we will have adjacent over hypotenuse now. Excuse me, opposite over adjacent. So the cotangent will be adjacent over opposite, which will be 3 over root 55. Now to clear that, we can rationalize that denominator. We can multiply the numerator and denominator by root 55, and we have 3 root 55 over 55. Okay. Let's review some identities. We have gone over all of this, but I'm just going to make sure that you review these. And we talked about the sine squared plus the cosine squared is equal to 1. This is very useful. This one you won't see too much, the cotan one, but what do you notice? It follows along. Tan squared, cotan squared. There's your 1. Secant squared, cosecant squared. So as you can see, this is just the co of the one above. So you want to use this one with co, okay? And we've gone over all of these reciprocal identities. You will need to know these. And so you'll need to know these as well. Okay, let's go to number 12. Given, and this is our last problem in the section, given the secant of theta equals 41 divided by 40 for theta in quadrant 4. So it's a good idea to go ahead and get this written. And we know we're going to be in quadrant 4. Now, in quadrant 4, we know that if we have the secant of theta equals 41 over 40, we're going to have to now solve for the tangent of theta first, okay? So, or we'll go ahead and use our properties over here to the right. Let's do that first. So we have the secant of theta is 41 divided by 40. And that's also equal to 1 divided by the cosine of theta. So what does that mean? That means that the cosine of theta must be 40 over 41. Okay, so we do need to know that. And we can now have that the sine squared of theta plus the cosine squared of theta is equal to 1. And you may need your calculator for this, or you might be able to follow along. And if you work that out, you'll have 1 minus 1600 divided by 1681. And I got that the sine squared was equal to, whoops, 81 over 1681. So if we take the square root of both sides, we will have 9 and we will have plus or minus the square root of 81 divided by 1681, plus or minus 9 divided by 41. Now we have to decide which one that we will choose, plus or minus 9 divided by 41. That's the sine of theta. Now, keep in mind, in quadrant 4, the sign is negative. So therefore, the sine of theta is the opposite of 9 over 41. Bring that up just a touch. Okay, so we took care of the sine of theta already. Let's go ahead and work on the tangent of theta. Okay, and then I'll show you on the sketch where this theta is equal to that. And we can just, now we know we're in quadrant 4, so we could probably just go ahead and put that there. So what do we know in quadrant 4? We also know that the tangent is negative in quadrant 4. So let's do a little work for the tangent. We know that the tan squared of theta plus 1 is equal to the secant squared of theta, and that's what they gave us. They gave us that the secant was 41 over 40, so we now know that this is 41 over 40 all squared, and we can subtract 1 from both sides. So we have 41 over 40 squared minus 1, and that's 1681 over 1600 minus 1, and you will have 81 divided by 1600. Why I wrote that so big. So what do we know now? That if we have the tangent of theta, it will be plus or minus the square root of 81 over 1600, which is plus or minus 9 over 40. We do have to choose the negative value. So we will have that the tangent of theta is the opposite of 9/40. And what I'll do is I'll put a star up here by these. Whoops, I wanted to use. And I'll put those there. Okay? And that concludes this section.